We've seen the proof that every complex operator can be put in Jordan form, meaning it has a Jordan basis. And now we wonder, how can we actually compute one? And you may guess, well, there's probably not a simple method which is guaranteed to work, because the proof was not so simple, and that's actually a very good guess. And if you search online, you will find many recipes of how to compute, how to find Jordan bases, and most of them are not guaranteed to work. And the one which is guaranteed to work will be more complicated than this simple list of instructions. And it's so hard actually to find it online that I wrote myself one way which is guaranteed, and later on I will show you also another way to find Jordan bases. But before, let's start with these methods, which I call quick and dirty. So they're very quick, they're very simple, easy to remember, relatively, compared to the other one that will come later. And maybe they work, maybe they not. So I gave them this funny nickname. So the first case, makes more sense, I would say, when you have multiple eigenvalues, it will be the following. Find the eigenspace. So how do you find the eigenspace? You just solve this equation. Write down a basis to this space. And for each vector on that basis, you do the following. You try to go backward and solve this equation here. What is this equation here? This is basically saying n v prime equal v. And so you solve this equation. And then you get the solution of this equation, and the solution of this equation, you place it here. And you solve again this instead of v. So instead of v, now you use v prime, and you solve again the same equation for v prime prime. If you can solve it, then you solve again the same equation, and then you get some v prime prime prime. And then you keep doing this. Well, at some point, and this will arrive necessarily, at some point you will have no solutions. You'll find out that this equation here simply has no more solutions. And at that point you stop and you move back here to the next vector, to the next eigenvector in this basis that you found. And you do this to that vector as well. And now look at the whole collection of vectors that you got. And this whole collection of vectors will be associated to that lambda. Now you come back here and take another lambda, repeat the same process again, and then you get, let's call this lambda prime now, then you repeat again the same process, and then this will give you a collection of vectors for lambda prime. And you do this for every other eigenvalue. And how to use this method, you now take all these vectors that you found here. So you started with a basis for the eigenspace, and for this base, solve the equation, found another vector, solve the equation, solve the equation, solve the equation, found a vector, no solution, no solution. So this is what you found. So now you want to list this basis in the right order. So you take a vector and take this one. Now again, you take a vector, take this one, and take this one, now take this one, and this one, and then this one. So you list the bases in this order. And this will be, if you have enough many vectors there, this may be a Jordan basis for your operator restricted to the generalized eigenspace corresponding to this lambda. And if in the end, when you collect all these vectors listed in the right order and all these vectors listed in the right order, and then you move to the other eigenvalue, etc., maybe this will give you a Jordan basis. So this is the first quick and dirty method that may or may not work. At least it is simple to describe.